Hello everybody, this is Dr. Pennington again, and I'd like to talk to you more about voltaic cells in this video. You will hopefully have just watched the first voltaic cell video that talks about how you can actually take something like this and draw it out in a very simplistic fashion. I didn't really talk too much in that video about what's actually happening here, so let me try and expand on that a little bit. Alright. Whenever you set up a voltaic cell like this, and if you remember, a voltaic cell is one in which a spontaneous redox reaction occurs and the flow of electrons that spontaneously happens is picked up by the light bulb or the voltmeter or whatever it is that you set up. So in theory, if you set things up right, you can take a piece of metal and its salt and its nitrate salt, put that into a beaker, take another metal and its nitrate salt, put that into another beaker and hook the two up, and maybe you'll see some sort of voltage produced between the two. Now that's not always the case, because not every metal will necessarily produce a spontaneous chemical reaction. There has to be a way for us to know what metals will produce a spontaneous reaction, and ideally how much voltage will be produced in each case. And that's one thing that we can figure out from this video. It's one of the things that I'll talk about. But there are several things here that we need to make sure that we understand, and we'll talk about in this video. For example, how do I know that the anode, or what actually is the anode? How do I know what's the cathode, and what does that mean? What does the plus and minus mean? Why do the electrons go this way? Why don't they go the other way? Just what exactly is happening here? Which is the best way for the electrons to flow? Which way will I draw them wrong? You know, that's an important thing for me to know. Most importantly, what the hell is going on here? Alright. From what you've seen before, you know that for a redox reaction, as we've seen in class now, a redox reaction is split up into two half reactions, one oxidation and one reduction. So in the oxidation reaction, the electrons are lost by the starting species, and those electrons are picked up by the reduced species, and the whole process just sort of continues. All right. So in one cell you always have to have an oxidation, and in the other cell you always have to have a reduction. It doesn't matter which, as long as you have one of each. You see, you can't have a redox reaction with two oxidations. You cannot have a redox reaction with two reductions. You've got to have one or the other. Now, in the oxidation at the anode, you'll always see the species, the metal strip, losing electrons. That's what oxidation is, losing electrons. You remember the mnemonic oil rig? That's absolutely still true here. Oxidation is loss, reduction is gain. So when the zinc loses electrons, part of that metal becomes zinc 2+, which is water soluble, so it goes into the water. In other words, the zinc shrinks a little bit, and that's shown on a molecular level here. The original pieces of zinc, when they undergo oxidation, they will come off the zinc strip and go into the solution of zinc 2+. So over time, this zinc strip will shrink. The reduction, on the other hand, is where you take copper ions from the solution that gain electrons and form copper solid, and thus add on to the outside of the copper. And that's actually what will happen. So the size of the cathode will actually increase, at least in theory. So the anode will always shrink and the cathode will always increase in size, which is fine if you want to get more of the metal that your cathode is made of. Alright. But one thing that you always want to remember is, how can I correlate the arbitrary word anode with oxidation? How can I correlate the arbitrary word cathode with reduction? Well, I have another mnemonic here for you that might help. I learned this a couple of years ago and it seems to be beneficial. I don't know if it's quite as useful as oil rig, but it works. So think of this sentence: an ox and a red cat. I'm not saying you would have an ox and a red cat together at any time, but just bear with me. An for anode, ox for oxidation, red for reduction, cat for cathode. An ox and a red cat anode oxidation, or anode oxidation reduction cathode. Alright, so think of it that way. But how do we know that putting these two is going to light the light bulb? How do we know this is going to produce a, first of all, spontaneous reaction, and how do we know there's going to be enough voltage to light the light bulb? Well, the assumption is here that you know what the voltage is required to light the bulb, and that you know what, or you can calculate the voltage produced by the reaction, and that calculation is what we're going to do. In order for us to do this, there is a table of things called standard electrode or reduction potentials. I will call these myself standard reduction potentials. Alright, book calls them standard electrode potentials, but they're the same thing. You'll notice that all these reactions are written with the electrons on the left hand side. They're all written as reductions. If they're oxidations, the electrons would be on the right. Alright, and each of these reactions that has had its value of voltage here experimentally determined, so it can be put into this list, each of these reactions has a particular voltage associated with it. Alright, when actually run against something that has a standard potential of 0, which is the hydrogen cell here. But what's important is all these numbers. Some are positive, you'll notice, and then some are negative. When you are combining these two cells together, you're actually looking to get an overall cell potential. Alright, the little 0 here of course means standard conditions. E is potential, so cell potential is the overall voltage of the cell. And for a spontaneous reaction, this is what's important at this point, for a spontaneous reaction you need a positive value of your cell potential. So for a voltaic cell that always talks about spontaneous chemical reactions or spontaneous redox reactions, we always need a positive value for our cell potential. And this is what's going to make use of this table a lot easier, because we know the two half reactions that are happening here. One's oxidation and one's reduction. However, this table has everything written as reductions. So what we need to find is zinc and zinc 2+. I have to find the reduction potential for this, and then the reduction potential for copper and copper 2+ as well. This is where we have to be a little bit careful, because if we look for zinc, for example, where is zinc? Well, actually, let's just look at copper. Here's one entry for copper. Here is another entry for copper. I wonder, are there any more entries for copper? It doesn't really matter whether there are any more entries for copper or not. The issue is we actually have 2 entries for copper here, and the question that we have to ask ourselves is, well, which one do we need to use? I know we have copper solid in my reaction because that's right here, and I've got copper 2+ as well. And then, well, I can see, well, that gives me copper 1+. I don't have that in my reaction anywhere. I have copper solid and copper 2+, 2 electrons. That's the one that I want, and that has a standard reduction potential of 0.34 volts. More importantly, positive 0.34 volts. Oops. So the other one involves zinc. So let's go back to this table and find zinc. It's where we have to be careful and just scroll on through, because zinc's going to be in here somewhere. We just got to find it. Zinc, 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 zinc. Ah, there it is. Zinc 2+, zinc solid. That's the one I want. And 2 electrons. Good. The reduction potential for this is negative 0.76 volts. Alright. So what this means then is that I have this reduction reaction, copper 2+ plus 2 electrons going to copper solid, has a reduction potential of positive 0.34 volts. Now the same thing for the zinc the reduction potential for the zinc going to zinc solid has a reduction potential of negative 0.76 volts. Alright. I have to somehow combine these two to give me a cell potential which is positive. Now notice that both of these are, as I said before, both of these are reductions. But if I have a redox reaction, one of these needs to be an oxidation. The question is, which one is going to be my oxidation? Well, as written, neither. So I have to flip one of these. Now, from what we've seen before, you flip a reaction and you do something to the sign of it as well, and you flip the sign. And it's absolutely true here. So the question then becomes, out of these two reduction potentials, which one do I flip? With the rationale being I need an overall positive value of my cell potential. And hopefully you can see it's the one with the bigger negative value that you always have to flip. Because if you flip this one, get negative 0.34, you add those two together, you get a negative value of your cell potential, which would not give you a spontaneous reaction. However, if you were to do this, and say, if I do this, and put my two electrons there, I've flipped my reaction, so therefore I've also flipped my cell potential, or my reduction potential. Now, I add these two together, my electrons cancel out, I get my overall redox reaction, but more importantly, I add together the reduction potentials to give me, in this case, this would be positive 1.10 volts. And if we just think about this, we cancel that out, and so the overall, oh, I'm sorry, I shouldn't have canceled that out, I should have canceled that out, because actually we have got rid of this one because we flipped it. So my overall reaction here then is copper 2 plus zinc goes to zinc 2 plus and solid copper. Now you remember what we were saying before. The copper solid increases in size and the zinc decreases in size. And that's exactly what we're saying here. The zinc disappears and forms zinc 2 plus. The copper 2 plus disappears and forms copper solid. Alright, so this is a spontaneous redox reaction because of the positive cell potential. Alright. So just that's essentially how you manipulate these reduction potentials to figure out how you get the overall positive cell potential. But just one thing about what this negative and positive sign means, alright? Because you can't really have a negative flow of anything. Alright? Again, the sign is really all to do with direction, but it's a little bit more than that here. When we go back to here, the sign of this really tells us something about the strength of an oxidizing or a reducing agent. Alright? What this means is, the more positive the reduction potential, that means the better the oxidizing agent. Notice the red arrow goes up to the top here. Stronger oxidizing agent, the more positive the reduction potential. On the other hand, right down the bottom here, the blue arrow points down here saying the more negative, the stronger the reducing agent, which kind of makes sense. Larger negative, stronger reducing agent. Larger positive, stronger oxidizing agent, because they do exactly the opposite. And something that's a really strong oxidizing agent is also going to be a weak reducing agent, as you would imagine. So what that means is, the stronger or the more positive the reduction potential for a particular species, that means the better the oxidizing agent. In other words, the best oxidizing agent in this whole table is, well, what would you guys think? Which would be the best oxidizing, the best oxidizing agent? Well, the best oxidizing agent is the one that gets reduced the easiest, which in this case is F2. Alright. And so, on the other hand, the more negative the reduction potential, as in lithium plus having the most negative reduction potential, it means it's the much better reducing agent. Alright. So that means lithium is the best reducing agent. Alright. So, what this ultimately all means is you want to look for the magnitude and the sign of your reduction potential, with the idea that you're going to combine it with another one to see how your combination can come out as overall positive, because that's what you're really looking for. So let me just give you an example here. What if I was to say, what is the standard cell potential for the following redox reaction? 3Pb2 plus 2 solid chromium goes to 3Pb solid and 2 Cr3 plus. Well, we have no idea about this unless we can find some way of figuring out what the reduction potentials are. Alright. One thing that you should not worry about are the coefficients here. Alright. Yes, there is more lead than there is chromium, but whenever we talk about redox reactions and the voltage associated with them, you're talking about the rate with which electrons pass a certain point. So the actual amount of electrons involved is irrelevant. What that means is, if we can say Pb2 plus 2 electrons goes to Pb solid, that has a reduction potential of, let's just find it. Let's find it. Notice there is lead here, but that's lead oxide. We're not worried about that. Pb2 plus 2 electrons goes to Pb solid. That's negative 0.13 volts. That's probably going to be the one that we switch. That's negative 0.13 volts. The point that I was making here was, if I multiply this whole thing by 3 to get from 1 to 3 here, I don't make any change to my reduction potential. Simply because I'm not looking at the total electrons, I'm looking at the rate with which they're passing a certain point. So therefore the actual total amount is irrelevant. So you multiply this by whatever factor, the reduction potential doesn't change. In fact, the only way the reduction potential can change is if you flip the reaction, then the sign flips. It's the only change you can make. Now, if we look at the other reduction potential, that of chromium 3 plus, I guess that will be plus 3 electrons to chromium solid. I'm hoping everybody sees where that came from. I've got chromium 3 plus here, chromium solid. Or, if you want to do it this way, you can say chromium solid, just going off the overall reaction here, goes to, hang on a minute, goes to chromium 3 plus. And if that's 0 and that's 3 plus, that must mean 3 electrons. You can say, well, I know this is an oxidation, because the electrons are on the right. Therefore, when I look this up in the table, the sign of what I write here is going to be opposite. Or if we look up in the table and say, well, that's the value from the table, let's reverse it because we're reversing that reaction. But let's find it first. And again, we're going to have to be careful because we've got to make sure we find chromium 3 plus and not something else. So, chromium 3, chromium 3. Well, there's 2 of those, but which one do we want? Well, we want the one that ends in solid. So therefore we want that negative 0.73. We don't want the one above it because that ends in chromium 2+. So that's negative 0.73 as written. So therefore that is negative 0.73 volts. So if we were to flip it the way we have done down here, this would then be positive 0.73 volts. Now you remember when I first wrote this one down, I said because it's negative it's probably going to be the one that we flip. Well, notice that that wasn't the case because this one ended up being more negative. If you were to flip this one, add this to this, and you would still get a negative number. So you want to flip the one with the biggest negative number, which is this one in this case. Alright? So now we can, I'm just going to put a line through here because we're not using this one anymore. Alright? Now, of course, 3 electrons, 2 electrons, those don't match. We have to make them match and multiply the whole thing by 3 here, the whole thing by 2 here. But remember what I said? Because voltage is a measure of how quickly electrons pass a certain point, the actual total number is irrelevant. So even though I'm going to say this, I'm going to multiply all this through by 3, it makes no difference to the reduction potential. And even though I'm doing this, it makes no difference to the reduction potential again. So therefore the cell potential in this case is simply this small negative one plus the bigger positive one, meaning that's 0.60 volts. And that is how you figure out the potential for any galvanic cell or any voltaic cell. Alright? Okay. Alright, that's it. So we have talked about what it is, what all the pieces in a voltaic cell, how we can recognize the anode, how we can recognize the cathode. We talked about the fact we have the oxidation and reduction reactions. We talked about the standard, using the standard reduction potentials, looking at the number and magnitude to figure out which one you flip to become the oxidation, and thus figuring out from that how you add these together to get the overall value, the overall cell potential, and that should say cell. And remember, we also said a positive value of the cell potential is what we want if we're looking for a spontaneous reaction, which is what we are looking for in a voltaic cell. Alright, thank you.